x is less than or equal to 0. If 0 is less than x is less than or equal to 2. And my last one, x greater than 2. What, guys, is f of x discontinuous? Any suggestions on how to do this? Any recommendations? You do this on a test. What do you recommend? I bet you all have great ideas. Look at this thing, it's a piecewise function. We saw this earlier today. We saw it with the limits, right? What was our strategy? Graph. Y'all want to graph it? Yeah, let's look at the graph. What would mean that it's continuous? It's connected, right? If it's any broken piece, then it's not going to be what? Continuous. That's all we got to do. Will that work? Now when we're done, I say we look for easier ways. Does that sound good? That's how we're in class. So let's take this. All we're going to do is make the graph. We know how to make a graph. Let's make the graph. Make the piecewise graph. But when we're done, let's look for easier ways that you could say, wait a minute, you know what you only have to do? You really only have to check the what? See, I want to think about it. For continuity, we're only concerned about, aren't these smooth graphs? Yeah, it's a smooth straight line, that's a straight line, that's a parabola. We're really only concerned about what x values. X equal to 0 and the x equal to y. 2. So some of you might find it easier to just go, why don't you just check the zeros for these two, x equals 0, and check 2 for these two, and make sure they match. If they don't match, it's not connected. Right? For it to be connected, y value's got to equal y value. True? But I'm going to pretend like, hey, if you like making graphs, it works every time. Here it comes. All right, 2 plus x squared. I want to make a little table. What's going on at 0? 2, give me a number less than 0. Negative 1? What's 2 plus negative 1? All right, 0, 2. 1, 3. There goes the parabola. Ooh. All right. Make a little table. 4 minus x, plug in 0, what do you get? 4. Plug in 2, what's 4 minus 2? 2. All right. Straight line, right? Hey, where's the hole? Where's the hole? Where's the hole in the second one? Where do I put the open hole? The open circle? 0. Yeah, I want to put it right there. And let me just make sure you can see that. I really should put an open circle, all right? Open circle, closed dot. I already know one x value. Can we put it down for answer? What's one of the answers? Check it out. Where's that thing broken? What x value? Function is discontinuous at x equals 0. Do y'all agree? That's my point. That's how fast we can figure this out. All right, good. But we also got to check this what? 2. So I want one more, make the table. What's going on at 2? You plug in 2, what do you get? 2. You plug in a 3, you get a 3. Aha. But it's got, doesn't have an equal sign. But this thing was already closed up. So when do I put an open circle over a closed dot? What happens when you put an open circle over a closed dot? It stays what? It stays closed. I'll say that again. Look, I'm putting an open circle over something that was already closed. It stays closed. It's just still sitting there. And then at 3 you got up to a what? 3, and it just keeps going up. So everyone, what do you think? Is the function discontinuous at 2? No, it's continuous. Continuity, continuous means connected. Cool? Awesome. Hey, and in terms of L and C, everyone, if a function with limits, if a function's not continuous, can a limit exist? I think so. So first of all, if a limit exists, do you think the functions will be continuous here? Yeah. True? Can you say, this is a true statement. If a function is continuous at a point, the limit must exist at the point, right? Do you all agree? Yes. That's a true statement. Did you know you can write the contrapositive? It means you can switch this around and put the words not.
So I'm going to make another statement. Not L would have to imply what? Not C. You can write it that way. That means if a function doesn't have a limit existing, then what's going on? The function is not what? Continuous. Hey, one more thing before you leave. That graph. Great job with the graph, right? Is everyone okay with this? Guess what's going on later in calculus? We talk about a word, differentiability. See, that's continuous there. But differentiability, we're talking about how it has to be nice and smooth. And the idea that the slope from the left has to equal the slope from the right. Now, can you see the slope there? Isn't the slope negative? How about the slope from the right? It's positive. So that's our next topic that's coming up later. Is the function differentiable at 2? No. That's a later topic, because slope would have to equal slope. We can see, slope's negative, slope's positive. But, we just finished continuity, is it continuous? It's definitely continuous, it's connected, right? It's just a corner. That's not smooth. You follow me? Awesome. Hey, and before you go, who can hit it? Who had a fast way to do this problem? Without the graph. Could you do this problem without the graph?
Yes.
What'd you have to check?
Check 0 and 2.
Because you check the 0, do the numbers match?
No.
You plug in 0, you get 2, you plug in 0, you get 4, and he goes, okay, that's one of the answers. Then, like he said, you plug in 2 here, and you plug in 2 there, but do those match? Yeah, 4 minus 2 equals 2, and you go, okay, that's it. And you're done the problem. And that's your work. That's all you'd have to show, I'm serious. Okay? So if you're a hater of graphs, or you just want to save some time, do it that way. Have a great one. Super job.